So the goal here today is to do 3.1, 2, and 3. Friday we'll do 3.4, or Wednesday we'll do 3.4, and Friday we'll do the quiz on 3.1 through 3.3. And we'll do like a pause and review day on the following week and then take the test. Hopefully that all squeezes in before we have to leave for winter break. Okie dokes. So in chapter 3, we're going to be talking about sequences and series. So I want to start with just defining what we mean by a sequence. So last chapter we talked about functions, right? And like a function is just like some pairing from a domain to a range where we match up some x with some f of x, right? And we match it up in a special way where each x only goes to one specific f of x. So a sequence is still a function, but there's a couple of key differences. The first difference is that this domain is always the natural numbers or a subset of the natural numbers. So the only inputs in our sequence are going to be positive whole numbers, maybe 0, typically not. But like 1, 2, 3, 4, I can't plug in 1.5. I can't plug in 10.5. Can I plug in 4 over 2? Well, that's 2, so yeah, that's okay. But no negatives, no decimals. Everybody's okay? Now the range, the outputs, those can be any real number. So for functions, when we write function notation, we write f of x equals, and then we write like some formula in terms of x, like 2x plus 5 or something, right? Everybody's okay there? Where the x is like our independent variable, and then this stuff is like our y, that's like our dependent variable. Most commonly with sequences, we'll use like some lowercase letter and we'll use a subscript. That's like the independent variable. That's like the input for our function. And then we'll write that output in terms of n's now. That's like our dependent variable. So for sequences, we have the additional vocabulary. We call these independent variables. That's like the term number. So if n is 5, it would be like the 5th term in the sequence. If n is 12, it would be like the 12th term in the sequence. And the dependent value is like the term value. So we could say like if I said f sub 5 is equal 18, that would tell us that the 5th term in the sequence is 18. Right? That's how we read that statement. Is everybody okay with like the vocab and the notation? I think it's really important that I kind of show you that we're still really doing the same thing that we did with function notation, but the way we write it is a little different. And the way you read it, the vocabulary associated with it is a little different, but it's still operating the exact same way. Everybody's okay with that? So ways that we could represent our sequences, we could represent them as like just a list of values. Now, how many terms are there to this sequence? 5, right? Term 1, term 2, term 3, term 4, and term 5. So this is like my n. Does everybody feel okay there? So this is an example of a finite sequence because there are just 5 terms to it. There's not infinitely many. Now, we could write a similar sequence, and if I put the dot, dot, dot at the end, how many terms are there to this sequence? Infinitely many. So that's an infinite sequence. So sequences can be finite or infinite. Doesn't really matter. Feel okay? All right. So if I wanted to have you list, say, the first 5 terms, for, say, this sequence, what's the first term going to be? Well, I just plug 1 in for n, and I evaluate. The second term is I'm just going to plug 2 in for n and evaluate. I'll plug 3 in for n and evaluate. Plug 4 in for n and evaluate. And then we'll plug 5 in for n and evaluate. So we could say that my sequence B, I could also write it this way. Everybody okay with that? Whether I describe it as a formula or like a list of terms, they're both representing kind of the same information. Does that feel okay? What I did? The advantage of having a closed formula like this is if I say I wanted the 50th term, it's still easy to get. I can just plug 50 in and evaluate. And through the magic of being good at math, I can do that quickly in my head. 1 out of 50 is 2%. Right? Anyways. Okay. Kind of plugging along. So we can use sequences to kind of model real life behavior. So say we have a situation like the following. So we have a 180 liter bathtub containing 50 liters of water, and then we're filling it at a rate of 10 liters per minute. We ask how much water is in the tub after 5 minutes. When will the water overflow the tub? And if we say instead we have the drain that's opened at the very beginning, so we're filling and draining at the same time, and we're draining out at a rate of 15 liters per minute, as well as filling at 10 liters per minute. How long before the tub empties? So probably before I did any of these things, I would probably just try to write like an equation to describe what's going on here. So like the amount of water in the bathtub should just be 50 plus 10n, right? Where n is the number of minutes. So I have 100 liters then in the bathtub after 5 minutes. Everybody feel okay there? When will water overflow the tub? Well, I have to have more than 180 liters in there. So if I solve there, I get n is greater than 13. So maybe I say after 13 minutes. Does everybody feel okay there? You're okay with arithmetic in your head? Here, now we have the water coming in. We also have the water going out. So if I look at that net, it's like minus 5n. And for an empty bathtub, that's going to be 0 liters in there. So when I do that, I get n equals 10. So it's after 10 minutes, the bathtub should empty. You guys feel okay here? Again, this is basically like an Algebra 1 story problem, or just like a linear equation that we're dealing with. Now, there are two major types of sequences that we'll talk about. The first type is arithmetic. When you hear arithmetic sequence, you should really just think linear function. So the way to describe an arithmetic sequence is, where did they write the formula in here? Oh, they hid it over here. Okay. I can describe it with the explicit formula this way, or I can describe it with a recursive formula this way. Each of these has their own pros and cons depending on the formula. The explicit formula is nice because you can find like the 10,000th term right away, just plugging 10,000 in for n. The recursive formula is nice because the calculation is really easy, because all you're talking about is like what is the change from the previous term to the next term. So it's very easy to write that one, but if I want the 10,000th term, means I got to have the 9,999 terms before it computed, which if you're a computer, no problem. That's pretty easy for me to do as a computer. As a human being, boy, that stinks. So this is just the first term, right? This is the previous term. That's what that means. D stands for common difference. I'm just going to abbreviate that CD. And I want to just point out to you that this equation here is one we've seen before. So if you guys remember, that's the point slope equation for a line, right? If I rewrite this using the point, comma, 1, A1, which is like the output from a sequence, right, where the n is the independent variable, and that like a sub 1 is like the dependent variable. And I write this instead as like 1 n comma a sub n. So that's like I just add the a1 to both sides. I notice that that is exactly the same formula that we just wrote above, except instead of having a D, there's an M. What is that telling us? That common difference is just acting like the slope. It's essentially, it means the same as a slope. Hi, how are you?
Hi, good, how are you?
Just fine, thank you. Alessa, that's for you. All right, so let's take a look at some sequences, showing you guys how to determine whether a sequence is arithmetic or not, and then how to find the formula for it and all that kind of jazz, okay? All right, so let's say we have the sequence 2, 11, 20, 29, 38, and then 47. So if I have a sequence that's a list of consecutive terms like this, to check that it's arithmetic, what I'm going to do is just look at the difference between each term. So 2 plus 9 is 11, 11 plus 9 is 20, 20 plus 9 is 29, 29 plus 9 is 38, 38 plus 9 is 47. So I know this is arithmetic because the common difference is constant. If that D was different at any point, it's no longer arithmetic. But that tells me the common difference is 9. So already I have a way to write the recursive formula. I could write a sub n is equal to 2 plus I should say a sub n minus 1, excuse me, plus 9, but I have to say where the sequence starts at. So I would say then where the first term is 2. Or I could write the explicit formula. So a sub n is going to equal the first term plus n minus 1 times d. Or if I distribute the 9 through and combine some like terms, I'd get 9n minus 7. These guys are equivalent. There's no difference in the answer there. Either one is fine. If I wanted, say, the 50th term, though, which one would I want to use? The explicit or the recursive? Oh, the explicit. The explicit is our shortcut to go to, if I'm looking for a big term number, that's what I'm looking for. So that's like 443 or something. If I wanted just like the next three terms, the recursive would work just great, right? I'm just going to add 9 to 47, and then add 9 to that answer, and then add 9 to that answer, and that'll give me like my next terms real quick. So the recursive is great for next terms. The explicit is great for like way out in the future term. You know what I'm saying? Just feel pretty easy, right? Basically just writing equations for lines again. You know what I mean? Let's look at a little bit different. Let's say I want the explicit formula for the recurse or the arithmetic sequence. When the first term is 5 and the fifth term is 11. Hi, Miss Anderson. How are you? Thanks. This is essentially asking you to do the same thing as write the equation for the line, given the 0.15 and the 0.511. What do I need to do that? I calculate the slope, or in this case, the common difference. Right? And then, because I have the first term, I can just do that, and I'm done. If I didn't have the first term, let's just say we wanted to use this one, what I would prefer to do is just treat this like a equation for a line using like the slope-intercept form. So I'd say like 11 is equal to 9 times 5 plus b. And I'm just going to solve for b. Oops, not 9. I'm in the wrong problem still. 3.5 times 5 plus b. So that's like 7.5. So I subtract that over. That's like 3.5 is equal to b. So I'd have a sub n equals 3 over 2n plus 3.5, or 7 over 2 if you want. Does that feel okay? It's just writing equations for lines. It's exactly the same thing as we just did in chapter 2. Just writing the equation for a line. It is super simple. One thing that the IB loves to do is to kind of like make financial related questions out of these ideas. So you will see story problems similar to like Susie decides to deposit an initial amount of $1,200. I'm going to just change everything into dollars into a savings account because I don't want to have to draw this symbol for like euros or whatever these things are. On January 1. The account pays 5% simple interest on the initial amount. Assuming no further deposits or withdrawals, how much money is there in 10 years? So again, we're just going to write like a arithmetic sequence, or like really just a linear equation. So the I'm going to have, yeah, it doesn't matter. So I'm going to have 0 as the initial. And then we're going to pay 5% each year on that, 5% of that $1,200 each year. Or you could write it as like this way. It's the same formula either way. So if I just want A of 10, this is not right. Don't do that. That's just not right. That was going to be an insane number. Oops. I made a mistake when I did this. Can anybody see what it is? Yeah, so year 0 is the initial deposit. Year 1 will be like this. So but if I call this n equals 1, what do I really have down here at year 10? That's really n equals like 11, right? Oopsie daisy. Oh my gosh, okay. Nothing's working for me this morning. So some mornings I just turn my tablet on and it just won't find the Google Drive for me for whatever reason, which is super cool until you want to use the Google Drive and then you're like, oh, where is it? Gosh, that's still not the right number there, is it? I'm so dumb. All right. That's my D. That's like the interest there. Good golly, Miss Molly. So this is going to be like $1,800. Jeepers creepers. All right. That was a mess. My apologies. Another example. So let's say we have the sequence where like I know the 50th term is 6, and the 51st term is 11, and the 52nd term is 16, but I want the first term. What I am going to do is I'm going to write the equation for the function and then plug 1 in to find that first term. So again, I'm going to think about this as like the points. Right? Those are just points. But I can see what the slope is, or the common difference. How much are we changing by? 5. So I'm going to say, okay, well, 6 is equal to 5 times 50 plus b. So b is going to be negative 244. So my equation is going to be that. So if I want a1, so that's negative 239. Okay. All right, moving on. The other type of sequence is geometric. When you hear geometric, you need to think exponential. So our explicit formula here and our recursive formula and this R is called the constant ratio. So let's just again look at, given some information, can we come up with the constant or the values and the constant ratios and everything else like that. All right. So let's say I have this sequence here. Right away, if I look at this, I can tell it can't be arithmetic, because if you look at the signs of my terms, they're alternating from positive to negative, right? Immediately, you know you're not going to be adding or subtracting the same thing over and over if things are jumping back and forth from positive to negative. So what I'm going to look for here is a constant factor for multiplication. And I see that negative 4 times 3 is negative 12. And negative 4 times negative 12 is positive 48. And negative 4 times positive 48 is negative 192. And negative 4 times negative 192 is positive 768. So that tells me this is geometric as opposed to arithmetic. Remember, arithmetic is adding and subtracting. Geometric is multiplying or dividing. You don't want to think about division. You don't want to think about multiply by or reciprocal. Even if you're like, each time we're dividing by 2, think about it as times 1/2. Okay? So just always think multiplication. So my explicit formula is just going to be the first term times r to the n minus 1. Or my recursive would be 3 times the previous term, where the first term is 3. That's my recursive. Does that feel okay there? So the most difficult kind of problem here is if we want, or if we ask you to, okay, if I give you the geometric sequence, it contains like, oops, I didn't mean to change that. Who's like, third term is so if I give you something like this is like the hardest situation to deal with. So the way you would do this is, again, we're going to think about these as points. And I'm going to take my equation or my my geometric formula here, where I is just going to be any term rather than necessarily having to be 1 being the first term. So like 243 is equal to a sub I, well, no, let's just, that can be 1. That's fine. I'll just make that 1. Times the r to the 3 minus 1. And then similarly, I can say 3 is equal to a1 times r to the 7 minus 1. I'm going to make a system of 2 equations with this. So I'll call that equation A and equation B. Now notice in this system of 2 equations, unlike things we saw in section 2, instead of my variables being added, my variables are being multiplied. To solve this system, I'm going to divide the 2 equations. So I'm going to take equation B and divide it by equation A. I always pick the numerator of my division equation to be the bigger exponent. It just is going to make the arithmetic a little bit easier. So when I do that, the a sub 1's cancel out. 3 divided by 243 is 1 over 81. R to the 6th divided by R to the 2nd is R to the 4th. I do the 4th root of both sides. That picks up a plus or minus. So this is R could be plus or minus 1/3. Why did I pick up a plus or minus? Because the root was an even root, right? Cube roots, 5th roots, you don't need a plus or minus. Square roots, 4th roots, 6th roots, you do. So I'm going to take that then and plug that into either equation A or equation B. I'm going to choose to use equation A. The nice part is that for equation A or B, because it's an even power, it doesn't matter whether you plugged in positive 1/3 or negative 1/3, the squaring is going to make the result the same. So that's going to give us 1/9. So if I multiply both sides by 9, then I get 2187. So I'd say then that my recursive or my explicit formula, well, I just do that. Or I could write it that way. Each of those should be listed separately as they're both technically correct. That's kind of the worst situation. The other thing they like to give you here is going to be these like financial problems. Again, here we're going to see compound interest instead of simple interest. So the compound interest formula is generally written this way, where A is the account value at some future time n. P is the principal or the initial investment. R is the interest rate written as a decimal. So if it's a 10% interest rate, you have to write as 0.1. Sometime T. N is the number of compounds per year. So in the problem, I might say compounded annually, that's N is 1. Compounded monthly, N is 12. Quarterly, N is 4. So just, use your word sense. And T is time, and usually that's going to be in years. All right, so let's do a couple quick examples, and then we're going to be done with this section as well. Sound good? All right. All right. So Samantha or Sam puts $15,000 in a bank account earning 6% annual interest compounded monthly. How much is the account worth in 20 years? So I'm just going to use that formula from before. My P is 15,000. My R is 0.06. My N is 12. And my T is 20. So just into my calculator that goes. So I get $49,653.07. Why didn't I round to 3 sig figs here? It's money, right? It's money. I'm going to round to the penny. The second part of this question asks how much interest was earned in that time. So what do we start with? 15,000, right? Everything else in the account must be interest. So I just take that and subtract my initial investment. So I get $34,653.07. How's that sound? Not too bad, right? Let's say instead you have $1,000 and want to I want to double that in 10 years. What interest rate do I need, assuming it's compounded quarterly? Okay, so here I'm going to still be using that same formula. So N is going to be 4. P is 1,000. Double that, 2,000. That's my A. And so now I need to solve for R. Oh, and 10 is T. So I'll start by dividing both sides by 1,000. Now to get that, I'm going to have to do the 40th root of both sides now. I'll subtract 1 from both sides. And then multiply both sides by -4. And we will get oh my goodness, guys. Great googly moogly. This is a plus sign here. Plus, 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 minus, plus. That's better. It's like, that doesn't seem right. Oh my great googly moogly. Here's the problem. Okay. And the force goes there. Yeah! Not your best day, Kulik. What can I say? We all have those off days, right? Now when I type this in, now I'll get the reasonable. There we go. So I need about 7%. Feel okay. So you guys should work on sections 3.1, 3.2, and 3.3 homeworks. Next time we're going to do series, so we're going to be adding up the terms of sequences next time. It's fine. Again, just remind yourself that all this stuff is basically just Algebra 2. It just got like different symbols or different names to stuff, but it's still just like the stuff you would have done in Algebra 2. So it shouldn't be too bad. If you remind me on Wednesday, I'll show you how to do some of this writing the equation stuff with your calculator. I just couldn't do it today because for whatever reason my computer can't find my Google Drive. But how's that sound? Okay? Who's going to remember to ask me to do that? Who's in charge? Bryn's going to remember. Who's going to remind Bryn then? Alessa. Okay. Sounds like a recursive argument there, but or circular argument, but that'll work. I'm happy with that. All right, I'm gonna stop here.